Yeah, and I won't be here on the Tuesday following the fall break. And I didn't hear anything back from people. So if you want to hear exams at that time, you're free to come out here. Otherwise, there'll be no one here to do anything on Tuesday. On Thursday, Professor Payne would do a guest lecture. The paper should be on the list, right? You should continue to do the enter on the Blogspot thing. And I told him that he could read the peer review before he comes to class. Right? Make sense? I should have email access, though I may not be checking often. I will be internationally roaming, so I don't know if I'll check quite often. So yeah.
Will the midterm be due then when you're back the following Tuesday?
Yeah. Yeah. I think I had it like Tuesday or Thursday, but next Tuesday. Yeah. I expect people would do that over the break.
Okay. Well, I mean, if it's Tuesday after break, I'm not trying to extend it. I just.
Oh no, it's not, because I'm not going to be here, so I'm not going to look at it, right? So I have no incentive to get it from you earlier than that. And hopefully you can use that time for your next project, right? And if you have any ideas, like talk to me. I'll be here over the break. Email, I'll look at it, right? Anyway, so this paper, this is one of the paper which talks about a shipping product, which is quite popular. It's currently out there. And I think we have it installed on one of the lab machines. We have a grant from VMware which lets us play with any the VMware products. So if you want to explore more of this stuff, you should be able to use it in the lab. I'll let you know how that works, and maybe it can help you too, right? But reading your comments, I had a feeling that most of you didn't know what a virtual machine was. And you're mixing virtual machines with the notion of multiple processors and shared memory between multiple processors, which are kind of similar, not so similar. The idea of virtual machine is sort of similar to what you're talking about for microkernel and all those things. It's trying to solve somewhat similar problem. It's trying to run something, right? So how many of you have used a virtual machine? Quite a few, right? Which is kind of surprising because the reviews didn't seem to reflect that. So what machine did you guys use? What's the product?
Parallel workstation.
Parallel, okay. On a Mac, I guess.
What?
On a Mac?
No, Windows.
On Windows, okay.
I use VMware ESX.
You use this one, okay.
I use VMware workstation on the Vista running a Linux.
Okay.
I use a Microsoft virtual machine.
Okay. What is I actually don't know what is Microsoft virtual machine?
It's just running Windows.
Under Microsoft.
Yeah. So I can have like two copies of XP and this stuff.
Okay. So, and how many of you use Zen? There's somebody who's used. So there are different products out there, which essentially all they try to do is they create the abstraction of a physical machine, virtualize the whole machine, and to a form where you can install your own operating system, where you can run another operating system on top of another operating system, right? So the idea here is you have sort of your real OS, and then so you have the hardware here. This real OS virtualizes the hardware, so it looks like a virtual hardware here. You install your new OS, called guest OS, and you can do multiples of these, right? And this is another OS, and this is another OS. In the wildest form, you can have this is like Linux, and this is XP, and this is XP, or what have you, right? And that's the idea. So you have this sort of this hardware, sort of this real operating system, and so on and so forth. And different virtual systems kind of blur some of the stuff. You don't have to have this strong notion of a hardware, real OS, real guest OS, and all those things. Zen kind of makes it a little bit, Zen is not truly running an unmodified operating system. Zen requires some sort of a cooperation between the guest OS and then the real OS. So the key here is, if you do it this way, the way I drew it, there's complete fault isolation, right? Because if this guest OS crashes, all it can crash is, if it crashes the whole hardware and everything, it can only crash this component. Everything else should be able to run, right? So if you want to run 3 processes and they want to cooperate with each other, and you're worried about fault containment, you could potentially put one process here, one process here, one process here, and those processes can talk to each other. If one of them dies, your underlying system keeps running, right? That's sort of what you can do, and some of you may have used it in that sense. If you feel that Windows XP is not stable enough, you virtualize it so that if it crashes, you're still okay because only your virtual stuff died and you're able to proceed, move on, right? Is there another reason why you personally have used virtual machines for your own use, other than fault containment? Yeah.
I worked at a company where our software could only be installed once on a machine, but sometimes I had to do development on different versions. So I had, on my main machine was the newest, was the development version, but then I had virtual machines for every past version that I might have to do like bug fixes or testing on.
So what you're pointing out it exposes 2 different components, right? One of the components sounds sort of you're trying to violate the software agreement, which only lets you run one process on a machine, right? So I'm not sure.
It wasn't a legal thing. It was that the software was designed. I don't know if it had to do with the registry or some kind of shared file.
Okay.
You could run 2 versions.
So if your software, that's a good point. So because I didn't want to touch the other part, right? So if your software is written to fully assume that the whole machine you can muck around with, then this is a good version, right? And the other point you mentioned, if you have different versions of the operating system, rather than having that many physical machines, you can create virtual machines for different operating systems, and then hopefully you can go back and forth between different ones and debug and test and what have you, right? So this idea is not actually new, right? This idea was sort of one of the first things that people did after they started building computers. And so in the 60s and 70s, virtual machines were all the rage, and in fact the IBM mainframes still continue to have that sort of model, right, where they virtualize the underlying hardware, and which is the IBM mainframes essentially do that. So they virtualize this hardware so you can run your different operating systems on top of that, right? And this made a lot of sense back then, because back then the operating systems were not multi-programmed. They were not designed to run multiple programs in the same way that we do. Like they're not time sliced and stuff. So instead of, rather than building an operating system, or the time for time sliced operating systems had not come yet, so they built operating systems which didn't know about multiple programs. So each operating system can only run one program. So once you did like this, then essentially you're doing what we do for multi-program systems, right? We have 3 different programs running in their own virtual machine. So you get to time slice between those 3 virtual machines, which essentially gives you the multi-programming that we're used to, right? So when it started out, their goal was operating systems back then only ran one program. If you want to run 2 programs, you virtualize them, and then you run with that, right? And the thing which helped them back then was this heavy hardware support for doing that. All the IBM machines supported this in hardware, so they could do this in a fairly efficient fashion. So they didn't face the performance penalty of virtualizing that we would see in modern machines, right? And but the flip side is it could only run one program, which was fine back then, right? And then it went out of work, because then people started building operating systems which can run multiple programs. So there is no reason to do all this stuff when you can have one machine which can have different programs or what have you, right? And one of the things which started happening in the 90s is we began to have lots of servers, lots of machines which were idle, right? We began to have this notion of clusters, and so what happened back in the IBM time was the hardware is very expensive. You have to do this virtualizing so that you can run multiple programs, and then hardware became cheaper. So it didn't make sense to do all this virtualization. You can actually put one machine in each person's desk. So this went away. But then, as time went on, the things that you put on your desktop became more and more powerful. So now they were becoming more and more powerful. Now they became multiple processors, and you have clusters of machines and stuff like that. And at that point, you wanted the operating system to keep up with that and be able to treat this cluster of machines as a single operating system, right? And that was not happening. The vendors were not doing that. The Microsofts and all those people were not doing that. And the other problem was, once you went into a large distributed system, if one of the machines crashed, you had to worry about how to bring them back. And the machines were the operating system was not good enough to contain the faults and all those things, right? So rather than build one operating system, if you assume that each chair is a different hardware, rather than running one operating system which control all these machines and run it all together, the idea was to create this notion of a virtual systems, right? And the whole impetus was to create these virtual systems that can then communicate with each other, that can then do fault containment and stuff. Then I don't have to worry about what the underlying operating system does. I create a virtual machine on top of it, then I can create multiple instances and so on and so forth. So this idea came back in the mid-90s with a project from Stanford called DISCO, which this paper refers to, right? It had 2 SOSP papers, and then eventually that company was spun off. It was primarily developed by Mendel Rosenblum, who's a faculty at Stanford. He spun off the company, and then they changed the name from DISCO to VMware. So we are studying something which came out of Stanford. So they refer to this that paper a lot because that's where VMware came about, right? So that's sort of the history of where things happen. And it took off for a lot of different reasons, right? It took off not for the reasons that I talked about in terms of multiple distributed systems and all those things. It took off for the reasons that you guys mentioned, right? The commodity operating systems are crappy. They fail a lot. So this lets you do development much faster and so on and so forth. So it took off for different reasons than what it was supposed to have taken off for, regardless, right? So now it's a very popular kind of system, right? So one of the primary uses that the people use is the one that you mentioned, where you run it on your desktop or something to get a bunch of stuff. The other good use for this kind of technology is in cluster computing or a distributed service, right? So essentially now, some of the systems, some of the people tend to buy their own set of machines and run a distributed system on top of it and manage those and all those things. So like Neurodym has the CRC, which has multiple servers, and they manage those and stuff. But most folks don't want to maintain all the stuff in-house. They go to a data center. They go to a data center which will potentially have lots of machines and stuff, right? So the idea here is, I form a company, maybe AOL or something, I form a company where I buy enormous amounts of machines, right? And then I rent them out to other people, right? And that's sort of the model that the world is kind of in right now. And this model is called different things at different periods of time, depending on what is cool, right? So it could be called cloud computing today or what have you. The idea here is there's lots of machines, and I want to give it to somebody, right? So what I can say is, you as a customer can come in and say, I want 1,000 processors, right? So I can say, I'll give you 1,000 processors. I go through a notion called SLA, which is a big deal, and that's itself a thing for research, right? It's called a service level agreement, right? So we both agree on what we should get. So you can say, I want maximum of 1,000 processors, I want this much CPU time and what have you. Then I take your money, right? So then I have to give you that many machines, right? So if this says I need 1,000 CPU hours, right? Or you can say I want 1,000 CPUs or something. Depending on what you say, I need to give you that, right? So the naive approach to do that is for me to go ahead and buy 1,000 processors and install whatever operating system that you need, install whatever I have to do, and give them to you as 1,000 different machines, and let you use that, right? So that will service your SLA because you asked for 1,000 processors, and I give you 1,000 processors, right? And that's not a good business sense because essentially if you're not using it, I'm going to waste all this stuff, right? So what they want to do is they have a large form of machines. They virtually create 1,000 processors for you, right? So and in that sense, the virtual machine system comes into play again. So I have to find 1,000 different processors which can run your operating system, right? Rather than install your particular operating system on the raw machine, I give you 1,000 instances of virtual machines, right? And I as the vendor put your virtual machine on a different system. So I can say you want thousands, I'm going to put one here, one here, one here, one here, and so on and so forth. And the fault containment means that I can put 2 virtual machines on the same machine, and as long as the performance is good, you're happy. So you could be running with a competitor on the same exact hardware, but you won't know because you have no. It's completely. If you believe this model, there's no way for you to access something else running in your competitor. So you guys could be on the same exact machine, physical machine, but the virtual machine gives me the facility to contain both your files. You guys have no access to each other. So I can have 2 untrusting clients on the same machine. I can move these things around because essentially, if I store all the state into a say file system or something, I can move your virtual machine from one machine to another machine, and you won't know any difference because your application is running on your virtual machine, not on the underlying hardware. So I can move these things around, right? So in terms of what the real world folks, this is a very powerful mechanism, right? So essentially, this lets me run on machines that I have no trust over, right? So I can run my application in Google. I don't have to trust Google, right? Because Google does not. So I'm running on my own virtual machine, not on Google's machine. I don't have to trust who else is running there, right? So this machine may be running, this virtual machine may be running somebody else, your competitor's application, but you have no way of knowing who they are. They have no way of knowing who you are. So the only challenge you have to deal with is the notion of resource management, which is some of the things that this paper addresses, right? So before you come into this, to this paper, the idea here is you can run all these virtual machines on the same machine. They're completely isolated. They can solve one of the biggest problems that we are dealing with at this point with the data center model. And this is the way to go about doing that. Does that make sense? Right? So this is far more important than what we used it for our own self, because this makes the whole data center a lot more feasible rather than installing and running this machine. So the technology exists where they can bring up, start up a machine. It doesn't matter what operating system it does. As long as you can run a virtual machine, I can ship a virtual machine to you and start the process and do the stuff, right? And this is becoming so popular that most of the newer Intel machines and Intel and AMD have hardware support to help some of this stuff. So they have extra instructions which help with this virtualization. So this is not a fringe stuff. This is a part of the main server computing that you would work on, right? So in fact, I don't know actually. So does Condor use Zen as an integral part, or it might use it? Okay, but all the grid computing, all those things, they like this stuff because then I can ship my job to somebody else without worrying about the containment really comes into the picture, right? So let's worry about what's the resource management issues here, right? So many of you mentioned that. So let's look at one single machine. Many of you mentioned that memory is not something that we need to worry about because memory is cheap. So we don't understand why they worry about memory, right? I mean, this paper is focused on memory, and that's why I sent it to the memory system class, right? So there could be 3 things that you worry about, right? There could be memory, there could be storage in terms of this, and there could be CPU, right? Those are the 3 major stuff that we talked about, right, on a particular machine. I guess the network resources, right? So these are the machines, these are resources that would be available to this particular machine. And so this particular hardware now runs 3 different guest operating systems, right? So the question is, do real modern systems, do you have to worry about all this stuff, or are they already solved, right? So in real operating systems, memory is practically plentiful, right? So if you, I think Apple released their laptops on Tuesday, so the standard configuration has 4 GB of memory, right? Which used to be a lot of memory, but 4 GB is considered to be the base, and actually that's the only memory you can take. I mean, this particular hardware can only take 4 GB, but 4 GB ought to be plenty for anything, right? So desktops, you can have a lot more memory. It's fairly cheap enough, but you ought to be able to have 8, 16, or what have you, right? So let's assume that you have 32 gigs on your server, right? Would that make this paper invalid, right? So this paper is fairly recent, right? But still, it's not that recent. I mean, it's like 5 or 6 years. So right now, compared to when this paper was written, is memory big enough that we don't have to worry about this stuff, right? So meaning like, we are good with memory, right? And same for storage, right? Storage, this paper does not talk about it, but we can conjecture what happens, right? Storage, if it's running on a single machine, the storage resources are much more plentiful, right? I saw a 1.5 terabyte desktop hard drive these days, right? So storage is plentiful, and CPU, right? CPU, we are getting more and more cores, right? So let's assume that the normal core is like 8 cores, right? It's a dual processor, 4 core each or whatever, so you have like 8 core or so. And network, we still stuck with 1 gigabit per second or something, right? So going from the backwards, right? So do you think memory would be a issue that maybe this paper or some other future paper would address for virtual memory systems? I'm talking about memory capacity, the network capacity, right? Do you feel that 1 gigabits per second is plenty of memory network for one server? So we are kind of, it's sort of serverish kind of machine, so would that be enough? Or do you need more? And is there something that we need to specifically worry about here?
It seems that we could definitely limit the performance of 1 gigabit is way not that much.
So how would you solve it?
Everyone just add more network cards.
Yeah, you can add more network cards, right? But I think the network is not usually the problem, because the problem with all these data centers are there are two kinds of communication, right? Communication between those machines and communication between that machine and the rest of the world, right? The rest of the world is not improving as much as these things, right? So we're not getting as much memory systems. The network from your home is not getting faster. So the network amount of data which is going into Google is not improving as much as the other stuff. So we are kind of okay, and between those systems, you can have more network cards, and we are sort of okay, right? There are other issues with terms of how to build high throughput systems, which are not specific to VMs, right? So the problem here is if you add 10 of these cards, right, most machines cannot deal with that much of network packets going through. Whether you have VM or not, one machine dealing with 10 gigabits per second worth of data is still a challenge, right? So beyond that, I don't think the VMs actually add much more because of how they may be used, right? There may be issues, but not in the general case, right? CPU, right? So hopefully these things are virtualizing one CPU. So let's say this is one CPU, right? So in the case I talked about with the 8 core, this particular system might be fine, because even if I statically allocate one CPU for the base OS and all this stuff, I'm still okay, right? So I can still add 4 more cores, and I should be fine, right? So CPU is always a problem, but in this particular case, the number of cores seem to be improving enough that it should be a problem, right? And yeah.
According to the data center in Notre Dame, they at peak hours from 8 to 5, they max at about 10% or so utilization of CPU time.
They use 10% of the CPU.
10% of all their server CPU time is used.
Okay, so
out of 100%, so that seems awful low. So it seems like they have way too much power for what they're doing. But
yeah,
it's not uncommon to have lots of extra wasted CPU cycles.
So in some sense, this is not related to what we're discussing, right? So is there a reason why we should run our own data center on campus? If the CPU is a bottleneck, right? We only use 10% of the CPU, right? So, I mean, clearly for us, CPU is not something we worry about, right? But hopefully, if you're running a data center, you don't want to run at 10%, right? Because that seems like an awfully bad investment, right? So you build this infrastructure where you can take 10 times the load, you only have 1/10 of the requirement, right? So you have to look at the peak, and if the peak is 10%, then you need to go find more customers. You need to find enough customers who can fill up the rest of the CPU, because you want to keep these things running as much as possible, right? One of the things that I think Google and that does is they can So if they expect something to come up in a couple of days, they can buy enough machines and then put them into the pool, right? So they don't have to keep them running all the time. They can, if they expect something is going to go up in 2 days, machines are fairly easy to get. You just call Dell or whoever, they ship a whole bunch of stuff to you, and all you have to do is those things have to run the barest minimum operating system enough for it to run a VM, right? So I just plug it in, so I can then ship a VM to it, and then I'm good, right? So 10% seems awfully bad because we need to either outsource our stuff or find somebody else who can use our stuff. So, but that's a good indicator, right? Storage I'm not going to touch here, right? Because the idea here is all the systems usually have enterprise kind of storage, which can scale to a large number, right? So even though if we talk about everything else as localized here, in the systems I expect that there'll be a big storage pool or what have you. So let's just assume the storage is not an issue, right? Which brings us back to memory, right? Which is the thrust of this paper. So if you have 32 gigs of memory, do you have to worry about memory at all? Would this be right? Seems like 30 gig memory, we shouldn't have to worry about the stuff, right? So what will happen to 30 gigs of memory? 30 gigs of memory still many of us feel is a lot of memory. So if we had this machine with 30 gigs of memory, and let's just say that since we have 8 core, right? Let's say we want to run 7 of these things, right? Just for the fun of it, right? How much memory would you need for such a setup? But each VM has its own dedicated processor, so each VM would be as fast as 1 core, right? So if the hardware support was there, and if the overhead for running virtualizing is very low, right? Each machine should be as fast as a real machine. You shouldn't notice any difference. And you could put all of them into a single desktop that you can purchase for fairly inexpensive cost. Is 30 gig enough for this machine or yeah?
Depends.
What does it depend on here?
Depends on what you're trying to do. As in every case, if each OS is okay with only 4 gigs of memory, then
so that's the key, right? So so when you have 7 of these, right? The question is, what happens to this 32, right? If there are 7 processors in a machine with 30 gigs of memory, I cannot imagine many applications which would need more than that kind of a system, right? So all the system things we did in our operating system is on managing memory between different processors. So if you have 30 gigs of memory and 7 processors, you should be happy for the most part, right? Except for some extreme cases, most of you should be happy because each one can get 4 gig, let's say, right? 4 gig of memory per process seems big enough. I mean, nobody should be complaining. In the general case, there may be cases where it fails, right? But is that what happens here, right? So the key is you cannot distribute the memory, based on the VM technology that we use, we cannot distribute the memory like that, right? So we may have to distribute it as, we may distribute like that. So we may distribute it as 4 gigabytes each to each of the virtual memory virtual systems, right? So once you do that, each virtual system only gets 4 gigs. So if you do a naive approach, right? If you do the naive mechanism that you talk about, however much memory you do, you have to allocate it among these different virtual machines, right? The thing which we like about the whole virtual machine, which is containment and not knowing anything, I mean, having these machines think that they have their own particular hardware also is the one which kills us, because if this machine does not know that it's running on a virtual system, it does not know it's running on a virtual system, which means that you have to tell it upfront how much memory it has, right? Because that's how machines are built. So when you build a normal machine, when you boot a normal machine, you have to tell it how much memory it wants, it has, how much physical memory it has. And most operating systems are not written where the amount of physical memory changes with time, right? So unless we have an operating system which can dynamically know how much physical memory there is, and if the physical memory goes away, it shrinks itself, right? So that depends on the guest OS, right? So unless you have a guest OS which can dynamically shrink and change their size, which most normal operating systems do not do, right? We are stuck with the fact that these operating systems assume they're running on a real machine. Real machines memory does not go down. I mean, real machines memory is a hardware resource which is there. So when they boot up, they try to ask the firmware how much memory they have, and whatever is told to them is what they assume they'll have, right? So when you run these things, the workstation virtual machines like the parallels and what have you, you have to configure to say how much memory each of them should have, right? And many of you may have done that, right? So you can say, I will have this one have one gigabyte, and this one to have 512, and this one to have 12 gigabyte or something, right? Right? How many of you done something like that, right? So once you do that, then you realize that this is the worst thing to do because this one probably wants to go more or something. So you're always trying to figure out what this number should be, and you're kind of stuck with that, right? So in the simple case, I can statically describe all the stuff, and then make sure that they all add up to 32 gig, and then we can run with that, right? Which is probably what we do. I mean, when in your machine when you're running a VM, you try to figure out how much physical memory you have. You allocate the amount of physical memory to different machines. So you're restricting how much you can scale. So unless you use something like ESX server, you don't understand. You don't really feel the problem that they're trying to solve, which is they want to be able to add more and give it more, right? So in the simple case, you can divide them all and say each one gets a 4 gig each, right? But what they want to do is, since not all the machines will use all the 4 gig all the time, right? Rather than statically allocating 4 gig to each of the virtual machines and use this machine this way, and rather than having only 7 virtual machines because the CPU is only good enough for 7 to be dedicated, I can actually try to go for 14 VMs, right? And so now I can have more VMs, and if not all the memory is being used, if statistically not all the CPU is being used, the same argument we use for virtual for processors, right? So then I can probably get better stuff out of it. So if I want to do 14 VMs, right, and if I can't give 4 gig anymore if I do a static allocation, right? So I would like to overcome it. So I would like to say each of the virtual machines get 4 gig, which means that 14 times 4 is the amount of memory that I've committed, right? So each virtual machine thinks that it has 4 gig. So what is 14 times 4, right? So that number, right? So each virtual machine, whenever it wants, it will get that 4 gig. And we have to do the tricks to make sure that we can run these different systems, right? We can support that system. That's what they're trying to solve here, right? I think it's still a problem because however much memory you have, the amount of memory that each operating system wants is also going up with that, right? So if Apple is going to ship their machines with 4 gig of memory, I can bet you that the next version of OS is not going to be optimized for 64 meg, right? Because they assume that the hardware is going to have that much memory. So the operating system itself wants that much memory. So you can continue to run those operating systems inside these virtual machines. So each operating system can have lots of memory. And our goal is to try to make sure that we can manage these things such that each virtual machine gets a lot of memory. And we do the tricks that we've already done in the context of virtual memory and stuff, where we try to make a larger memory appear onto a different process, right? So I think this problem is still valid, and let's go with that, right? So the next challenge is, I think some of you mentioned, so I think Ryan mentioned, right, which is, so what is the problem? Like, can you find out how much this is using, and can you go in and get this stuff? Can you go into the guest OS, and is that?
Sort of. What I was kind of thinking of is in terms of languages, when you're doing any kind of just-in-time compilation, you're going to find hotspots in the code, and you're going to try to optimize those hotspots as you see them. So one of the main things that they were saying was that when paging out guest OS pages to disk, because the actual hardware is under duress and needs more memory, that if you choose a page that the OS is going to page anyway, that was a problem, because then that page would have to come back into memory just to be paged out again.
That would be enough page.
Right. So the question that I had was, why can't you do something similar where you kind of, what the guest OS is going to run as the real OS, because you have access to the virtual machine. So can you do something intelligent like say, well, I kind of know that this thing's under virtual duress, and it's going to take time, but the question is can you amortize it over the cost of all the virtual machines so that you can say, well, I know this OS is going to bring this, I know it's trying to bring this page back into memory, but is it trying to bring this page into memory just to page it out again? And do some kind of intelligent prefetching of instructions or something like that.
So did that make sense? Right, the question he posed, right? So the problem is these guest OSs are something that we call it guest, but we don't know what they are, right? So in the extreme case, this real operating system has no way of knowing what this operating system is, right? So it could be a version of Linux that you compile to do certain things. So in that, so I can't really know what the OS is doing. So whatever I do here, right? So what I can do is I can do virtual memory for the whole 30 gig of memory, right? So I can decide to page things in and out over here. But what is happening is within this guest OS, it has 4 gig, right? So it could be doing paging in and out on its own virtual disk because that's what this operating system is doing, right? So if your process which is running inside the virtual machine, it's being swapping something in and out, and you are trying to do something in and out on the real OS, right? It's possible that you get double fault, right? So in that sense, you may decide to put something to disk, right? But this real machine the virtual machine does not know that you did that, right? Because there's no way this does not have any clue that you are there, right? So it will not know that you paged it. So it may try to write it to page, it may page it out, but the only way it can do that is it has to access the page to say, I want it to be flushed, right? So which means that here, you'll have to page it back in and give it to the OS and say, oh, okay, write it back to disk, and you write it back, right? So those sort of things happen because they don't communicate with each other, right? Right? So this one does not communicate with each other, and this should sound familiar to something we did earlier, right? Can you think of another technique we learned where the applications and the operating system communicate with each other back and forth, right? So the communication between the application and the kernel is a system call, right? What's the communication mechanism between the kernel and the application? Yes, so we looked at some of those techniques, right? So we can have this set of mechanisms where things can communicate with each other, right? So can you do that here? So where this can talk to it and this can talk to here. Where the real operating system talk to something here and vice versa.
You can't really do that without the guest operating system would have to know to listen for things from the virtual server, and it would also have to know how to talk back down to the virtual server, so it probably wouldn't work.
Yeah, it wouldn't work unless the guest OS is re-returned to know that it's running virtualized, right? And that depends on you trust, so it's up to the guest OS, and we can assume that not all guest OSs would do that, right? So in fact, most of them probably won't do that. So that way of going is not going to work, right? Even though in this paper they do violate those principles, but not in a full fashion, right? So the other alternative is what he mentioned, right? Where this OS, the real OS, knows what's going on inside the virtual machine, right? The virtual machine does not know that it's being virtualized, but the real OS knows that something is running in the virtual stuff, right? So it's free to look at all the memory state, it's free to look at all the process state, right? So can it look into the state and say, well, this is what it's going to do, and do what is necessary, right? Is that something that would be a feasible approach? Actually, I shouldn't say feasible because anything can be feasible because we haven't tried it out, right? But what do you think of that approach? Where the Big Brother OS is monitoring what you're doing inside your virtual machine because it has all the memory pages, so it can know what you're doing, right? So it also needs to know what you will do, right? It has to look at the page table. Let's say it looks at the page table to see that you're running at a memory pressure, So it knows that if the memory pressure reaches, like say 8% or some threshold because you're running Vista, then it knows that you're going to do certain things. So it can kind of make sure that it'll do the right thing for you at that point, right? That's sort of what you're saying, right?
Yeah.
Is that a good idea? Yeah.
I don't think so. I mean, violates is kind of theoretical. I think virtual machine, not to mention, now you have some policy in the virtual machine monitor that has to decide what notion of fairness is, and not to mention if you have 20 operating systems, you have to write something for each operating system.
Yeah. So I think your answer is two parts, right? One is it violates the policy that the real operating system should not look into what the virtual machine does. The other one is you have to do this for every different operating system, right? I tend to ignore the first one because, yeah, it's not supposed to, but the policies are designed by us, right? So there's nothing which prevents us from violating a little bit here and there if it can give you better performance, right? But the other part is you need to make sure that now you have to know everything about every operating system, which may or may not be easy, right? So if you have only one version of Vista, then this may be possible, but every patch, if you have to worry about every patch and everything, that may not be a way to go, right? But that doesn't mean that this is not going to be valid. So I think one of you mentioned that they use the Microsoft virtual machine, right? So if they have control over both the stuff, so if you have Microsoft and running your own virtual machine, so you know that you're running Microsoft and you know you're running Microsoft virtual machine, so they can know this knowledge and they can do something like up the start, right? But in general case, where you can run any operating system you want, where you can run FreeBSD or Solaris or anything under the moon that you want to run, we can't really have this communication mechanism because what you right now need is you need something here, right, which knows how to talk to the local kernel. It has to talk to your real kernel, and they both need to translate what they're saying, right? So it's easy to create such entity, right? You can make the user install something inside the guest OS, right? Which is sort of they call it a balloon. So I install something inside the guest OS, right, as part of the installation process for your system, and I can talk. I as the real OS can talk to that because it's just I'm talking to another machine. So I can talk to another machine kind of thing. I can talk to it and then say do this stuff on my behalf, right? The challenge here is if you want to work with this machine, whatever language this speaks has to be translated to whatever I understand, right? And so the power that we can exploit is limited to what it can do, right? They use one of these things, the balloon is essentially that, right? They use one technique to achieve this, which is they know that the virtual machine, that the memory that you have for a virtual machine is fixed when you initialize the system. You cannot change it dynamically, right? So what they do is they create, rather than be stuck with a little bit of memory, you create a larger virtual memory than what you may want, right? So if you wanted 4 gig, I give you let's say 8 gig. I make you install a balloon driver, right, which is essentially some driver which works on the guest operating system, right? It's not any complicated application. All it does is it tries to look for network messages, right? The one which is controlling it actually is this local machine, right? So when I need some memory from this process, right? So I tell this one to say, I gave you 8 gig, but right now I can only give you 4 gig. I can only give 4 gig to this particular operating system, right? So the operating system booted up with assuming that it's going to have 8 gig, but at this point I can only give you 4 gig, right? So I tell this to this balloon. This balloon is like a spy, right? So it listens to this stuff and it basically takes away half the memory from the local operating system, right? The way it does that is so it knows it has to take away 4 gig. It cannot tell the operating system, okay, at this point your physical memory is now no longer 8 gig, it's only 4 gig. What it does is it calls the privileged operating function inside your local kernel, right, and says I need 4 gig worth of physical memory, which I want to pin down, right? Pin down is something that you do for DMA access or something, which means that while I'm doing this stuff, don't touch it, right? So I ask for 4 gig worth of memory, and I pin it down, meaning that this OS cannot modify anything till I release it. So this way the balloon expanded and used up 4 gigs of memory. So as long as I know this is what happened, I don't page any of this stuff out, right? So essentially your program, your virtual memory now only has access to 4 gig of memory by having this little Trojan horse inside, which I control from outside. So if I say, okay, right now you can use all the memory, it tells the operating system, okay, I'm done with all these pages, so now it has those. Even though it's not actually using it, it's actually telling it to get access to the memory, right? So you can use tricks like these. So for this particular trick to work, what do you expect from the guest operating system? Can this run for any guest operating system? This balloon driver? Yeah.
Probably not, because the operating system can reclaim that without the permission of the balloon driver. That would result in.
Yeah, if the guest operating system does not support this notion that once you pin down memory, I cannot touch it. If that is not the case, then this won't work, right? If the guest operating system supported a notion where it can say, okay, you asked for 4 gig, but I'm going to take it away from you, then this won't work, because then it will try to take it out, take it away. Then bad things will happen, because now you're going to ask the 4 gig, and then bad things will happen, right? So this is entirely dependent on the particular the guest operating system, right? So depending on how you do this, so the way it interacts with the kernel is different. What can be achieved with the kernels are different. In general, this particular technique will work across for different operating systems, right? But you cannot do this for everything. So, it depends on you having folks, right? You might have noticed this stuff, right? You might have noticed it for the folks who use virtual machines, right? One of the things that if you're using a GUI-based system, it'll ask you, do you want to install Parallels utilities, or I don't know, they call it different things. They essentially let you install something inside the operating system. So they'll say you have to wait to install, you have to first boot into the guest operating system, then they go inside and install a whole bunch of applications, right? So they have to install all these applications which have to have good privileges, because it has to have privileges to do all this stuff. So that's a way for this real OS to project itself inside the guest OS to do some of the techniques that they want, right? Right? So anyway, so the problem here is, you can get all these virtual machines, and how do you manage memory is what this paper is trying to solve, and it's still a problem, because even though memory keeps growing, the amount of hardware, real memory keeps growing, the amount of memory needed by the different processors, operating systems also keeps growing, and the challenge here is, if they both can talk to each other, none of this would be a problem, right? If they can talk to each other, then they can basically say, when you start up, I don't have to give you a limit of how much memory you should have. I can only give you how much you want at whatever time. Then it becomes like a process model, right? Which we know how to deal with, right? If these two guys can talk to each other, then they can cooperatively figure out how much memory should be given to you. If memory is going to be taken, they'll do the right thing. But since they can't be expected to talk to each other, we have to do these tricks to make sure that the ultimate goal is, this operating system should not be, you should not expect the operating system to be modified, right? It's okay, you have to do this driver stuff to get into the operating system, but I cannot expect that Microsoft would do something so they can talk to me. And it's even more important because I can run any operating system I want. And one of the things that you mentioned, that you want different versions of the operating system and so on and so forth. So I want to be able to run different versions of operating system. I want complete flexibility in doing whatever I want, and this is how we do, right? And that's what I do. So they introduced 3 different techniques for kind of hacking this stuff. One is the notion of a balloon driver, right? Which essentially, it looks like it's growing bigger and smaller, and essentially that's a way for the real system to tell indirectly that you don't have enough memory, right? The hope is, once this takes up more memory, then your own guest OS would do whatever it does for when the system gets low memory, and that's good enough, because that's what you're trying to do. And what's the other 2 ones? The
Sharing.
Yeah, the next one, share, right? Which I think is a very important mechanism, right? The idea here is, this one has a set of virtual pages, this one has virtual pages, right? And if you can find out if these guest OSs, let's say, are the same operating system, right? So suppose you install 14 Microsoft OS, right? And you expect that each of the operating system will have their own DLLs and what have you, using the same piece of contents, right? So we may get more efficiency if you can figure out that they're all using the same exact contents, right? And I can sort of map one page to happen as three things, right? We do that all the time in a normal system, right? So if you write two applications which use a libc library, right? Libc library is used by all the applications in your system, so I can create one copy of the library, a libc library, and I can share it with any number of applications that you want, right? So I don't have to load that code for every application independently. So I can have one shared library used by everybody else, right? We want to expand that into this model, right? So if all of them are running the same Windows, right? They're running Windows XP, and they all want to load the same DLL, right? Let's say, I don't know, there's a thing called libc.dll, right? It would be nice if there can be one libc DLL for all the different systems, right? The challenge again is the point that these things don't talk to each other at all by necessity. So I can't really know what this is doing. I can't really know what it's loading, right? So this may want to load libc, but I don't have the contextual information to know that it's actually loading libc.dll rather than some junk, right? All I know is you're asking for memory. All I know is what memory contents are, but I don't know where it came from, right? If I had known something, if I could talk to the operating system, this operating system, if it were to tell me that, okay, I'm going to load libc.dll, then I can do something here, but I don't. All this kernel does is, I want memory, because it thinks it's talking to real hardware, so it's going to say, I want a memory, I'm going to write this to memory, I'm going to read it from memory, and so on and so forth. So I want to do something at that level to figure out what's going on and still achieve the goal of sharing the stuff, right? So since these OS cannot talk to me, what they do is they try to figure out, they go to the memory pages, right, and see if two pages are the same, right? The contents of two pages are the same. They don't know what these pages are used for, right? So it may be the case that there may be one page with all zeros, right, which may be used by libc, which may be used by your program to store something called buffer, whatever, right? They don't have the context. They don't know what is being used. All they know is this has one page with all zeros, right? This has one page with all zeros. If they find out there are two pages like that, they can map them into the same content and free up one of the physical pages used here, right? So they're trying to achieve what we do for virtual memory with this system, but all we have access to is the memory pages. So we have to have some kind of thing which goes every so often and figures out what pages you have and tries to compare the stuff, right? And you can't do this naively because it's a n-square operation. If you want to look at every page and find out if there's two pages which are the same, you can't do that because it's a pretty complex operation, right? So what you do is once in a while you calculate the hash of it, right? Hopefully a simple hash, and you use the hash to compare two pages. So if two hashes match, then you do the full check to make sure that they are the same page. If they're the same page, you map them, right? And then you use your typical copy and write to make sure that if they are modified by one, then you get a different one, right? So whatever we did inside the operating system, we try to do it as a hack over here because all we see is the memory pages. So once in a while I go see the memory pages. If two memory pages happen to be the same, then I try to map it into one and free up the other memory page. So I achieve some memory saving that way, right? So the memory pages, the savings I get is now I statically give you how much memory you wanted to boot up the system, but dynamically I remove some of the pages from you using the balloon driver, right? So if you ask for 4 gigs in this context, I can give you 4 gigs, but I'm over-committing myself, right? If I had to take some memory out, I use the balloon to squeeze you out and take the memory back from you, right? So that's one technique that they use. The other technique is, I know that 2 of your pages are the same, and it's especially true if I'm using lots of copies of the same kind of operating system. So rather than me since I can't talk to the operating system and figure out what's going on, I have no context to know what is really being shared, right? But I can look at the memory pages and see what are the same. If two memory pages happen to be the same, and I use the hashing to figure out, then I can map them to the same thing, and I have to do the copy and write trick to say, if one of them modifies it, I'll get another copies. So that way, I save memory. So this one will save memory. The first one will give you as much memory as you want to boot up the system, but what you actually have is dependent on what I as an operating system will give you, right? So those are two different techniques, and then they show that there are conditions why this works, right? And these are two different hacks, and the key here is the overhead of doing this is not hard enough, and that's the main thing. You don't want something to be so horribly compute intensive that you can't do this, you can't scale this stuff. But in the case that ESX server, that's what they do. So if you use ESX server, so they don't do this for the workstation that many of you talked about, right? If you have the VMware workstation, the VMware Parallels workstation, or what have you, they don't do any of these operations. So if you use one of those stuff, many of you may have noticed that you may have a fairly good machine, but if you run a VM, your machine will practically slow down, right? For the people who use virtual machines, right? What is the impression on running VMs, right? As you run more and more VMs, what is the impression of the system?
It's slower, especially the virtual machine itself is
Yeah, because so at the low-end systems, they do a static allocation. At the low-end systems, they give you one CPU core if you want it. But more important, in the low-end system, they give you all the memory you wanted. So whether you use it or not, right? But the ESX server, which is designed for a server, they can do different stuff. One of the stuff is they can give you as much memory as you want at boot up, but not really allocate to you. So if you run the workstation one, and if you look at the process status from your local this machine, it look like your machine is actually using all the memory it wanted. Whereas in the new model with the balloon driver, you will not use up all the stuff. I might give it to you, but I only give it to you virtually. I can take it away without actually talking to you using this balloon driver. I can do the shared pages. So if I have lots of this stuff, I can do this transparently to you. You as application have no idea this is happening. I'm reducing redundancy across these different operating systems, and depending on what kind of scenario you have, you can save a whole bunch of space, right? But the third technique they use is they know that each process has some pages that they're not using. So this is the notion of the working set, right? So they know that this virtual machine has lots of memory, right? That was given to it and it's using, right? And they know that there's probably some sort of a working set, right? Meaning that your particular program may be modifying these 4 pages over and over again, and then after a while they may modify certain other pages and so on, right? That's what your typical programs do, right? So they expect that normal machines may use a lot of memory. They expect that normal machines have programs which have working set, right? So their goal is to say, if I want to take away some page from you and page it out, right? It'd be nice if I can know this information and then try to page out these pages which you are using. It's idle because your working set is not touching those, right? If I can know this, I can page out pages that you're not using at all, right? If I can only talk to the guest OS, I can ask it, what is your working set, which it has to know, and what are you trying? So give me the accesses that you're going through, give me the places that you're going through, and I can figure out what should be done, right? Which is what the real operating system would do. But in the virtual memory system, I don't know what is going on because the guest OS may do whatever it wants, right? So you essentially try to figure this out using statistical sampling, right? You essentially go and see what pages got what changed, right? So you change the bits and all these things to be no access and see how many page hits you get. So if you see that these things are getting accessed, so the way I figure out what is happening is I take this sample, right? I as the real operating system take this sample and I make all these pages inaccessible, and from here, so when the guest OS accesses them, I get I see the reference to those, right? So if the guest OS seems like it's modifying, accessing these 5 pages, then I know that 1/4 of my pages are busy, 3/4 are idle, right? So I can use that to figure out who's having lots of idle pages and who's not having a lot of idle pages. And that's the third technique that you use. I don't know what your working set is, I don't know what is going on, I don't know what is happening. I sample once in a while, and if it looks like some pages are getting modified, then I think of you as you're more idle than the other one, then I try to act accordingly. Right? So I'm trying to find out, so applications have working sets, operating systems learn about the working set locally. Now the virtual machine monitor itself is trying to find out what your working set is using this mechanism. So I can compare 2 or 3 different virtual machines and say, this one has lots of idle pages, this one has like few idle pages. Then hopefully I can get rid of these idle pages and you won't notice. Your program will still get good performance because you are still in your, if I can somehow keep this working set, I'm still good, right? So maybe I can manage across the multiple VMs, right? So that's the third approach. So what's the problem with that approach? This is the problem that any working set systems have, right? Anything with a working set has the same kind of problem. What is the problem with with trying to optimize based on the working set?
Changed.
Yeah, the working set may change, right? So I hope everyone understands what the working set is, right? So depending on the particular application, it may go through one working set for a while, and then go to the next one, and then go to the next one, right? So while they're going through one working set, it may be going through one while loop or one loop, right? At that point, maybe only using this set of pages, right? But when they transition from one working set to another working set, then a whole bunch of other pages will be used. So it may happen that after that point, it may be using a different set of pages, right? So I have to constantly figure out what is happening, right? So during the transition, for sometimes it will look like these pages were hot and this page was cold because these pages were used a lot, right? If I keep using it a lot, let's assume they are hot, and if it's not used a while, it's cold, right? So if I've been using this a lot, this page will be hot. But the instant that I started to go here, that means I'm never going to go back to this page for a while, right? So this will look like hot because if you look at the past history, they were being used a lot. So this looks like it's going to be hot. This will look cold, even though if you wait a little bit time, I will start using this stuff, right? The problem with the working set is I have to look at the past to figure out what is my working set because that's how I know that this is being used a lot. But past is not necessarily an indicator of the future, right? Past is an indicator of the future while I'm inside the working set. But when I transition, past is not an indicator of the future. So I have to balance those stuff, and that's what they're trying to do here, which is something that you do in the real operating system too, right? So if I just look at the past, if I keep a long history of the past, I will find out the working set really well while I'm inside a working set. But for the transition, I will fail miserably because I'm going to look at something which was way in the past, which I'm never going to go back, right? I'm going to remember that for a long time, right? So the question of how far back do you have to go is a big challenge. And that's something they also show something here. But that's the fundamental problem, right? How do you know how do you know what your working set is, right? That's the real problem in any system. It becomes